So first of all, what I want to do is remind you what a Venn diagram is. So you may have seen this, I don't know, in high school or something. Okay, so these are a useful tool for understanding relationships between, let's say, 2 or 3 sets. If you go beyond 2 or 3 sets, there's not really a good way to draw a Venn diagram, but yeah, for 2 or 3 sets, it works well. So to draw a Venn diagram, so let's say for 2 sets, basically, how you draw it is you can make a big box, which represents your whole, the universe. So this is, yeah. So everything in that box is like, yeah, in the universe. You draw a circle. So let's say we have 2 sets, S and T. Okay. And everything in that circle, so the first circle is an element of S. So imagine you have a universe, maybe you have the numbers 1 to 100, or you have all the UVic students, or whatever your universe is. You can imagine you group all the things that are in S, and you draw a circle around it. Okay? And then you draw another circle, okay, where these things overlap, and that circle represents the set T. Okay? All right. So basically, these 2 regions put together represent the set S. These 2 regions together represent the set T. Now, in this picture, which region or regions would represent the set S intersect T? Yeah. Exactly, yeah. So this overlapping region here, so if someone says shade in this picture, the set S intersect T, what you would do is you would take this part, and shade that in, right? Because if this blob represents S and that one represents T, then this is the intersection of those 2 blobs. It's the things that are in both of them. So actually, this picture sort of explains why we use this word intersection, because it literally is the intersection of those 2 circles. It's the place they overlap. Right? What if we were to shade S union T? Yeah. Yeah, everything in both of the circles, as well as this inner thing as well, right? Yeah. So anyway, this is a nice way of sort of illustrating what different set operations look like, union, intersection, and things like that. How about if I did S intersect T T prime, complement of T? Yeah. Yeah, exactly. So I have to do some erasing now. Okay. So this would look like that because, yeah, it's all of the things in S. Basically, if you reason out what this means, it's all the things in S that are not in T. So it's things that are in S and not in T, which would just be this kind of moon-looking thing. Yeah? That's a good question. So in this case, it won't be, because here we say that it has to be in S and not in T. So in particular, it has to be in S. If I pick something here, it would be not in S. But that is a good question. Actually, I should do an example like that. So suppose I did, for example, let's do S union T prime. So what would that look like? Yeah. Exactly, yeah. So you can, that's sort of why we draw this box, so that there's something to shade in this case. So here you would shade everything that's not in the union. Okay. And there's zillions of different possible combinations you could have here, and you have to know which regions it represents. Any questions about any of that? Okay. Okay, so this was a Venn diagram for two sets. This is probably the most common one that you've probably seen before. You can also draw Venn diagrams for three sets. So this is my universe. So a Venn diagram for three sets would look like this. Let's say my sets are A, B, and C. Right, and similarly, you can, have more complicated questions similar to the previous ones. So if I said A intersect B intersect C prime, can anyone see what I would shade? Oh, it's going to be hard to describe in words. Maybe I'll just say it. So A intersect B would be these two regions here. Because, if you're just looking at A intersect B, it's kind of similar to the previous picture, right? You ignore C, it'd be these two regions. But then we're talking about the things that are in A and B and not in C. So this center region should not count. So it would just be like this. So it's all the things in A and in B and not in C. Yep. Oh, sorry, can you say that again? Okay, so if it was A union B union C prime, so yeah, you would definitely have A and B, like all of this. And then for union C prime, you would have the outside stuff. I'm not sure if that's the same as what you were suggesting or not, but yeah, so it's all the things that are in A or in B, so it's all of this, and then everything not in C prime, yeah, which would be everything outside of that circle. Yeah? We never looked at S union T prime, actually. I think we just said S intersect T prime. Yeah. Yeah. Because if I take a point outside of here, if you think about it, is it in this set? So to be in this set, it has to be in here or here or here. That point is in C prime, so it gets shaded. because it's out, C prime is everything outside of C. So that's outside of C, it gets shaded. In this case, it's not there because to be in this set, you have to be in A and B and C prime. But it's not in A, so it doesn't work. Yep. Oh, like why are like these? Those ones are inside C, but this is an OR. So if it's an A or B or outside C, and it's shaded because it's an A or B, yeah. Yeah. It's not quite C prime because, for example, that thing gets shaded, and that's not in C prime. So C is this whole circle, not just the stuff outside the, yeah. You'll get some practice with these things, yeah. Yeah, exactly, yeah. Okay. By the way, one thing to be careful of, so you can see I just wrote these intersections with no brackets or anything. That's okay if you're doing a bunch of intersections or a bunch of unions, you don't need brackets. I should just mention, if you have a mixture of intersections and unions, you need to use brackets. Because generally, if I wrote this, and if I change the brackets, these are not the same. So you do need to be, so here I didn't write any, I could have written brackets if I wanted to, but it wouldn't change anything. But here, if you have a mixture of intersections and unions, you have to be careful. By the way, you can technically do a Venn diagram for one set as well. So sometimes you might see this in your homework or your quizzes or something. Like, this is a Venn diagram for one set. It's just not that complicated. But okay. Any questions? Okay, let me, maybe we'll do more examples like this at the end, but let me now go through something called the principle. Oh, actually first, before we do that, I should say, I'll give you a bit more notation. So for a set S, let n of S be the number of elements of S. So for example, if I take the set 1, 2, 3, it's just counting the elements. So there's 3 of them. Something to be careful with, remember, well, actually maybe I'll ask you to guess what should the answer to this be. There's kind of 2 possible answers, but yeah, it's 2, yeah. So there's two answers you might think would be correct, but the correct one is 2 because, like we said, duplication doesn't count. So it looks like there's 4 things, but there's really only 2 because we don't count the duplicates. Yep. Because, so that's, yeah. So the notation is, like if S is a set, then we write n of S with the brackets. And to write a set, if you want to write the elements of the set, you have to write these brackets. So it's like, yeah, if this is S, it's like n of S. Okay. Let me now tell you about a nice formula for computing the number of elements in a union of two sets. This is something known as the principle of inclusion-exclusion. And specifically, this is the version for two sets. And then later, I'll show you how it works for three sets. So what it says is that for any sets S and T, if I want to compute the number of elements in the union of S and T, it's equal to the number of elements in S plus the number of elements in T minus the number of elements of S intersect T. So mainly, what you need to know is you need to memorize this formula, and you need to know how to apply it, when to apply it, and that sort of thing. That's the main thing to learn from this. But before we learn how to use it, let me just sort of give you a rough idea of why this is true. And I'm just going to do it basically with a picture of a Venn diagram. So this is S. This is T. Okay. So if I take S union T and I count the elements inside of it, so this counts everything. Let me number these regions. So region 1 is the outside, region 2 is this, 3 is this, and 4 is that. So it counts everything in regions 1, 2, and 3 once. Right? Yeah. Let me just do that. It's kind of a silly way to write it, but yeah. Sorry, yeah. It wasn't region 1. It should have been 2, 3, and 4. Okay. Well, what happens if I look at, let's say, n of s? Well, that counts region 1, or sorry, region 2 and region 3, right? So let's say I put like a little tick, a little mark here to say I've counted this once and I've counted that once. By computing this number, I count those regions once. When I compute this number, it counts regions 3 and 4. So now this has been counted twice. Everything in here was counted twice, and everything was counted once. Okay. So you can see I've counted everything, but this stuff got counted too many times. But to fix that, I can just subtract it, right? N of S intersect T counts region 3 only. So if I add those two things, imagine we kind of do some kind of adding these things. So like if I add these things, I get 2 times region 3 plus region 4. Then I subtract region 3, and it gives me 2 plus 3 plus region 2 plus region 3 plus region 4 will be left over. So if I look at N of S union T, and n of s plus n of t minus n of s intersect t, they count the same thing, and so they must be equal, right? If you count the same thing in two different ways, those things, the things you get must be equal. Whether you follow that or not is not particularly important. The main thing is to memorize this formula and use it, but this is a bit of justification, which, I mean, also this can help you to remember what the formula is if you know how to prove it. Yeah. Oh, yeah, sorry. Yeah.
Thank you.
No problem. Okay. So let's look at an application of this. Okay, so let's go back to languages. So let's say you have 100 students, 50 speak Spanish, 40 speak Turkish, 20 speak both, like both Spanish and Turkish. How many speak at least one of the languages? So when it says at least one, that means either speak Spanish or speak Turkish or speak both, right? So, right, so again, if we let S be the set of Spanish speakers, and T be the set of Turkish speakers, this says that the size of S is 50, the size of T, oh, sorry. I need to, sorry, this is our notation. N of S is 50, N of T is 40. Can anyone tell me what this last condition is telling me? Yeah? Exactly, yeah. So the number of things in S intersect T is 20. Okay, so this, if you are able to interpret this information, and you understand that, like, this is asking for the size of S union T, then you're pretty much done if you remember the formula, right? So we just compute the union has size, you know, I just plug in N of S is 50, N of T is 40, So these questions tend to be really, really long. That's why I've pre-written the example. So the question is, there's been a survey of 200 students. 62 of them are taking astronomy. 98 of them are taking biology. 146 are taking chemistry. 40 are taking astronomy and biology. 41 are taking astronomy and chemistry. 75 in biology and chemistry. And 27 are taking all three subjects. And then you're asked to compute how many people are taking at least one of the subjects. Okay. So when you're given a question like this, it's maybe good to set up, a few things. So I think it's kind of logical to say, I don't know, astronomy starts with an A. Let's call it the set of students taking astronomy. A, so this is the set of students taking astronomy. B is for biology. And just to save myself writing so much, I'll just do like this. C for chemistry. Right. And if I go through this, you can see, really what this 62 is telling you is that N of A is 62, right? It's the number of people taking biology. And so a lot of these questions are kind of the same. You just need to identify what the question's telling you. So N of B is 98. N of C is 146. Actually, can anyone tell me what the 40 is telling me? Yeah.
It means the intersection of astronomy and biology.
Yeah, exactly. So N of A intersect B is 40. Similarly, N of A intersect C is 41. N of B intersect C, you can see these things get long, is 75. You probably don't need to write it quite as much down as what I'm doing, but I'm just sort of writing everything down to show you. Okay. So is everything I've done so far, is it clear? Are there any questions about it? I'm just trying to interpret the question, basically. Okay. So similar to this question, when it's talking about people who, something at least one, so it's like saying how many people are in at least one of those three subjects, that's asking you for the union, right? It's people in astronomy or biology or chemistry or some combination of multiple courses. So we're computing N of A union B union C. We just use our principle of inclusion-exclusion formula. So I just take this plus this minus these things plus that thing. So 62 plus 98 plus 146 minus 40 minus 41 minus 75 and then plus 27. You got to remember which ones are minus and which ones are plus. which I almost messed up. Anyway. I don't have a calculator, but has anyone else computed it?
177.
Okay, I trust you. Does everyone agree with that? Everyone who's calculated it? Okay. 177. Right. Okay. So this is just a sort of, I mean, pretty much most of the examples you'll encounter will be just like this. I should say, again, though, you could get some variations here, right? You have this equation. You can solve for any of the different things in the equation. So we could have been given the 177 and asked to compute A intersect B intersect C, which you would compute and find out it's 27, right? So, yeah. By the way, a good way you can check your answer with these questions is by drawing a Venn diagram. Oh, by the way, actually, here's another variation of this question. What if I asked you how many students are not taking any of the classes? Yeah?
You subtract the total number of students and 177.
Exactly. So to repeat that louder, so what you would do is you take the total number of students, which is 200, and you subtract 177. So there are 23 students because, so 200 minus 177 is 23, I think, are not taking any of the three courses. Let me just quickly show you how to check your answer with the Venn diagram here, and then we'll be done. So the question tells you that there are 27 students in all three classes. It tells you that A intersect B has size 40, which means that there's 13 students in that segment, right? Because there's supposed to be 40 in total in A intersect B. 14 here, because these should add up to 41, because A intersect C is 41. There should be, how many there? 48 or something. Well, okay, to get this should add up to 62, and you keep going. And then if you count everything in all of these blobs in the middle, if it adds up to 177, you know you got it right. So